Any questions before we get started? Concerns, logistics? Great, okay. So, diving into the lecture, we're going to cover tokens. We're going to cover the ERC-20 standard. Some of you might have heard of it already. Kash is going to talk about smart contract architecture and upgradability. The last two topics are actually very, very interesting. They talk about a mentality of thinking about smart contracts and dApps in general that not many people think about today. It seems like, you know all these like great software devs who work on full stack or DevOps projects, at a full-time job, and it seems like as soon as they port over to the crypto space or the blockchain space, they forget all that. Smart contracts are something else, right? But they're not. People really should go into it with that same mentality of like thinking about the architecture, and that's what Akash is going to talk about. Anyway, so intro to tokens. A little bit of history about how we got here. How did we get to this point where we've got all these ICOs? Actually, it's not a new idea, right? Back when we had Bitcoin, there were token-like elements. Actually, back then, people considered those to be tokens. And things like we're talking about colored coin, which were layered on top of the blockchain protocol. And basically, you could assign an arbitrary label to a UTXO output and track every Bitcoin that was spent along those transactions and say, okay, this Bitcoin is tied to a certain asset, right? Whether that could be gold or a real-world asset, and you can say, okay, this is this color. Color is just an arbitrary label. Does that make sense to everyone? Okay, and that, yeah.
Was it ever actually tied to a real-world asset?
Yeah, so I think actually there's a company called Digix that does something similar with gold, right? Yeah, and so they're colored with specific attributes, and every Bitcoin spent can be traced back naturally because of the UTXO model that we talked about in the first lecture. Another aspect of this is smart assets, and smart assets are kind of a solidification of this idea, tying real estate to digital assets on the blockchain. For example, in Estonia, they use the blockchain to secure ownership of property. I guess the political situation in Estonia is kind of turbulent, and so they're afraid that some foreign power may invade at any time. And that way, they want to ensure that they have their property ownership right there on the blockchain, so that in the future, in the next year, they can still know, okay, I own this land, right? All right. And so we want to introduce some terminology, app coins and protocol tokens. And there is a difference, right? App coins, we've got this long quote over here. Basically what it says, it's a new model of financing a venture, right? It's exciting, it's hype. And obviously the person who wrote this was very excited because in the past, open platforms have been hard to fund, right? They've been difficult to monetize. To get people behind the idea. But with this new model of like selling your app, selling your token to fund the app, you get rid of the bootstrapping problem that a lot of startups today encounter. On the other hand, so that was an app coin, right? On the other side of things, a protocol token is kind of different. An example of a protocol token is something like Augur, with its reputation tokens, REP, right? And Augur is built on two protocols. So protocols are crypto economic mechanisms, right? For example, Augur is built on two different crypto economic mechanisms. One called the Decentralized Oracle Protocol, and the other called the Exchange Protocol. And the Decentralized Oracle Protocol provides a financial incentive for a network of nodes to arrive at a consensus around real-world happenings. And if anybody knows what Augur is, it's exactly that. It's a prediction market app. But what we're trying to get at here is that protocol tokens aren't limited to just prediction markets, right? Just because I came up with a use case does not mean it's tied to that use case. You could use that REP token for anything, And that's where the exchange protocol comes in. And so the point here is that nodes who participate in one protocol don't need to participate in the other one. And nodes who participate in the other one don't need to participate in the first one. Nodes have the choice of participating in both if they wanted to. The exchange protocol is just basically, I can sell you my token. And basically the way the prediction market works is that people can quote unquote bet on real life events happening. And that's the financial incentive behind using the token. And then they can trade the tokens, and that exposes different people to different happenings of the real world, right? Any questions on that?
So this
Yes.
is a protocol token or an app?
So Augur is considered a protocol token. By the way, these are informal terminologies. There's no one who's going to say, like, this certain token is a protocol token, or this certain token is an app coin, right? It just takes you to look at a token, to look at the white paper behind it, and to kind of categorize it based on what you think, right? And so Augur here is like one of the few clear examples of a protocol token. Can anyone think of an example of an app coin or another protocol token? I'm sorry? Gold? Golem, yeah, exactly. So Golem is tied to like this world computer mechanism, right? And so it's built on top of that usage. Okay. So moving on. What is the most basic idea of a protocol token? Ether, right? And Ether's incentive, right, is the smart contracts. It's people writing good code, right? It provides people the incentive to do that. So I guess you could equate things like Ether to like a fiat currency, and then app coins to things like the tokens you would get at a state fair, right? Generally, and this isn't a rule, this isn't a hard and fast rule, but generally app coins are less liquid, right? And more restricted in their use, whereas protocol tokens can be used for anything. And this is what we were talking about earlier, the issue of aligning incentives. Whereas traditionally, you'd have a situation with a startup where there was this bootstrap period, where you have to self-fund a venture, right? You have to raise capital before you become successful, right? The utility to user increases over time, but that's only past a certain point after you've iterated, and it takes money to iterate and time. With the token network effect, it makes things easier because you can finance things yourself. So a good analogy I've read actually is think about the internet, and say the internet was not funded by the government in its early days or by research, right? How would the internet come about? A company might want to sell domains, right? They would say, okay, in the future you will own these domains as long as you give us the money for it. And then the financial incentive there for people who contribute to that network is that the network should do well, so the currency appreciates, right? And that's what tokens are all about, right? Protocol tokens. Okay, so what's the issue with app coins, right? App coins need to be built on a protocol, right? And they're very specific. And so you get what's called the Metcalfe's law, the Metcalfe effect, where you have this graph right here, and you see a splintering of nodes across a shared protocol, or across different protocols even. Whereas with protocol tokens, you get the unified graph on the, I guess to you guys it would be on the right. With app coins, you get the graph on the left, if that makes sense. And there is some math behind it. I mean, generally, you can say that the value is proportional to the square of the nodes participating in that protocol. And then when you have the splintering effect, you sum up the nodes squared. But when you have different dApps built on a shared protocol, then the value of that protocol is unified. And the value of that is the sum of the nodes squared. So there's a difference. You've got the sum of the nodes squared and the sum of the square of the nodes. And the sum of the nodes squared is obviously greater. And on the bottom right, you can see that. Yeah.
Wait, so are you arguing that most companies should not have ICOs and just use a common protocol?
So most companies who use ICOs splinter the protocol, right? So if you have many different ICOs, like, so if for one investor to put money into an ICO, that means they're not putting their money into another one, right? And that's just the idea here. And it's called redundancy, this splintering effect, right? When you have multiple different parties doing the same thing here and there, you get this redundancy effect, which decreases the overall value. And here there's like solid economic theory behind why certain aspects of the market have gone ridiculous to the point that they're actually detrimental to the network.
So you're just saying that multiple projects that do the same thing are harmful to the network overall?
Yeah, on a very like basic level, yeah. No, redundancy within a product or project? It depends, right? If you're talking about a protocol, if you're talking about a certain aspect of a protocol. But in general, we'll just say redundancy is bad in this case.
So what exactly do you mean by the value?
Yeah,
Value of
that's a good question. That's a good question. Here we're talking about like monetary valuation. But really, it can be any sort of value. I would go so far as to say like the intellectual value, even, right? Like the interest, right? The potential benefit that you can reap from it. Yeah, and so another good way to think about this is talking about how app coins align incentives with investors, but have a net negative effect on the users, if that makes sense. So it's still a way of aligning incentives, but not with the users themselves. Okay, I hope that made sense.
Can you give us an example of redundancy?
Um,
Just the same, like the project is trying to do the same thing, or?
yeah. So actually, this slide is just for that. An example of a couple of interesting projects are examples of Golem was mentioned, Filecoin, also an interesting project. So Filecoin is interesting because it's a mix of both, right? It's a mix of an app coin and a protocol token, where the Filecoin was used, is used as a financial incentive, but is also used to get past that bootstrapping stage for the company. And the protocol here is storage, right? I don't know what the formal name for it, but storage is the name. And examples of looking out for red flags, maybe during an ICO or just in general after the fact, a lot of buzzwords. Buzzwords often signify a lack of substance, right? If someone just throws out buzzwords. A lack of a code base. Always be sure to check the code before you know what you're getting into, and this is specifically for ICOs. Mishandled ICOs, right? You've heard this story over and over again, I'd hope. People mess up, and that leads to a net negative effect on the network. One example of this is Bancor. That's why its logo is there. And then drama, and you can check out that drama over there. And generally, drama is a negative thing to have happen to a company. Okay, so moving on to the ERC20 token. This is like now the technical part of the lecture. There's this thing called an ERC, and that's the an Ethereum request for comments. And I guess you can't talk about that without talking about Ethereum Improvement Proposals, EIPs. And Ethereum Improvement Proposals are just like a bunch of devs getting together and saying, okay, this is how we're going to make a change to the network in order to improve the net user experience, right? And an ERC is when the community comes together and says, okay, let's decide on a standard to set to make the user experience better. And that standard here is ERC20, which is a standardized token template. And why is this necessary? Well, it's because $400,000 worth of tokens are lost currently, because tokens are sent to contracts that can't handle tokens, right? Aren't built for tokens. And maybe whether that's by mistake or whether someone is trying to purposefully burn them, different question. But the point here is that that number shouldn't be as high as it is, right? And furthermore, templates give developers a lot of freedom. It empowers developers to say, okay, now I know what this token is going to do. I know what this token is built for and what it can and can't do, so I know how to prepare for it. I know how to build a platform to facilitate its growth. And that's why we needed the ERC20 token. And this is what it looks like. If anyone's familiar with Java interfaces, it's pretty much the same. You just have a contract and a list of functions. You don't have to define the functions. That's what an interface is. It just says, okay, there are these functions with these inputs and these outputs, and they may be constant or internal or external or private and whatnot, but this is how you're going to structure every token henceforth if you want to comply to the standard. And so we've got, the general total supply, balance of, transfer, transfer from, approve, and allowance, and also two events. There are also a couple of data structures that are defined, and people generally, this isn't a hard and fast rule either. This is in more details. So let me just ask, what is the difference between transfer and transfer from? Does anybody know? Can anybody tell just by reading?
So transfer from is a way of transferring from an account that isn't necessarily the sender,
Mm-hmm.
and someone would have the account owner would have to call the approve function first,
Right.
or the allowance.
Right. So interestingly enough, the ERC20 lets you assign someone else as the spender of your tokens. Weirdly enough. And I was talking about that extra stuff. So these are some extra data structures that are defined and functions. So you need a constructor, right? Every contract needs a constructor. And what would you use a constructor for in a token contract? Maybe to define the initial amount, right? To set the total supply as something that maybe later can be changed by minting new tokens or cannot be changed. Maybe you want to have one supply and that's it. And then the two other functions, data structures, balances, to keep track of how many tokens everybody has, and allowed, to keep track of who's allowed to spend whose tokens. And that's going back to the idea of this transfer from method. And then you can iterate on that. This is what's called the human standard. And this is just additional parameters built on top of the ERC20 template. So things like name, the name of the token, its symbol, and the decimal places. So why 18? We're saying 18 here, which is the most common number. Why is that? Weirdly arbitrary, right? So that's the amount of decimal places Ether has, right? If you think about Wei, how that's 10 to the negative 18 to the Ether, yeah. And that's why it's the most common. But you can define it as whatever you want. It just denotes the denominations allowed in your currency. What's up?
Is there any legitimate way for for anybody to enforce people developing tokens in this, like, according to this API?
Yeah. So you can't force anyone to do anything on the network, right? But there is a way to incentivize people to use this template, right? And an example of that is Etherscan, right? Etherscan is a great website. It lets you check source code of contracts. It's got a bunch of nice stats and graphs and data visualizations. But also, if you want to standardize, if you want to be able to see specific tokens, Etherscan will only show ERC20 compliant tokens on a certain list. And that's because it just makes it easier for Etherscan to be able to show you information about that token because it knows what to expect, right? If you come up with a random token that isn't ERC20 compliant, that leads to problems with querying certain parameters in the token. And so Etherscan can't display that properly. And so there is an incentive. You are kind of forcing it in that way, if that answers your question. So I was just going to go over an example of how approve and transfer from works, because that's basically the most complex aspect of doing an ICO. And in your midterm, that's probably going to be the biggest technical challenge you guys face. And so this is the summary of the code, if you guys need it later on. But we're going to go through a quick demo over here. And so you have two users and a smart contract, an ERC compliant token contract. And we'll just call these address 1 and address 2. And address 1 has 100 value, and address 2 has 200 value. And so address 1 is going to call token contract.approve, and they're going to input address 2's address and 30 value, right? So now what happens is that address 2 is able to spend 30 from address 1's balance, right? Transfer is complete. And if you query it, if you query token contract.allowed with these two indices, because again, allowed is a mapping, you'll get 30, because that's how much address 2 is allowed to spend from address 1's balance. And you can see how this gets very complicated very quickly, because address 2 may also be allowed to spend 50 from address 3's balance, or 40 from address 4's balance. And they may have allowed someone else to spend 50 from their own balance. So you got to keep track of all that. Because if somebody spends somebody else's balance and they're not allowed to do that, you've got a problem. Right. So now token contract.transfer from. This is where that method comes in. If you wanted to spend from your own pool, you would just call transfer. But this is address 2 spending from address 1's pool. And they're spending 20 value. And so how many do they have left? How much value can they spend from address 1's pool? 10. Awesome. Okay, and if you query that, it's 10. Yes?
Can you approve more than you have access to? Like, can I approve, if I have 100, can I approve 60 to somebody and 70 to somebody else?
Yeah, so good question. Can you approve more than you have like access to, right? That's completely up to you to define, right, in your own token contract. Feasibly, you could do that, but you would have to account for the problems that it would lead to later on. And so that's your prerogative. And if there's a problem, people are going to come after you, right? If you do an ICO and you let people delegate more than they have to other people, how do you, then you need some sort of credit system, right? Or IOUs. And that builds another layer of complexity on top of things. Yep.
Is there a difference between someone like having tokens in their own account and being able to spend from another person's account? Like is the entire ledger just keeping track of from whose account you can spend, or do you also have your own? Like, what is the difference between having your own money and being able to use someone else's?
So the question is, what's the difference between having your own money and being able to spend someone else's money?
In the end, it's just like tokens that you can use, right?
Yeah, but in one case, you own the tokens, and in another case, you're spending someone else's tokens. Does that make sense? I'm not sure.
But wouldn't that also mean that you just have the ability to use them?
It just means you have the ability to use more tokens, right? For you personally, that's all that means to you, right? But like you have to think about what would incentivize someone to grant you access to their token pool, right? And then you can do a lot with that incentive. Some people build their entire token idea on top of that incentive to like be able to grant other people access. And maybe you don't want that functionality, but then it's not ERC20 compliant. Does that make sense?
I think he's asking like, what is the use case of
Oh.
this token? Like, what is like, why not just if you're allowing someone to use 30 because you want to send them 30?
Yeah.
Oh, I see.
What's the use case of that?
Mm-hmm. Yeah, that's a good question, and that's for you guys to decide. Like, in your use cases, this functionality exists, right? But it doesn't mean that your token necessarily has to build on top of it, right?
Like, are there any common tokens like Gnosis or Augur?
Yeah. The biggest like factor I can think of is that it just saves time, as opposed to having a transfer and then having to wait for them to receive it. Then you can just say, okay, just go ahead, spend this much, and then you can revoke that at any time, right? Maybe you don't really want them to permanently own your tokens. Maybe you want to say, okay, today I'm going to let you access my pool, but tomorrow I'm going to revoke that access, right? And if by that time you haven't spent my money, that's your problem, right? Maybe you don't want them to permanently take your tokens. Maybe you want to give them like a chance.
Or maybe you want to give them like, you can spend up to this amount for whatever thing, but then after
Sure, yeah, exactly. It's
that, money up front and then hope that they return something.
yeah. Well, yeah, exactly. You don't want that situation, right? What's up?
So in this form of transaction, it would show up on the blockchain as being transferred from their account, right?
So it wouldn't necessarily be a transaction, actually. It might just be a state change. Actually, it would be a transaction, but not in the sense that it's a transaction
Let's say
with
the
ETH.
stuff that they're giving you access to.
What's up?
Say if you use the ether that they're giving you access to,
Well, it would be the token.
the token.
Yeah.
But if you use the token they gave you access to, would that be coming from their account then?
If one more time?
If you use the token they gave you access to,
Yes.
and you transfer that to someone else,
Yes.
does that transfer show it's coming from their account?
So the transaction would say, so that's a good question. This is what would show up, right? It would say that you made a call, account 2 made a call to the contract, transferring from account 1's balance pool,
Okay.
right? Okay.
But it's still marking that you made that call.
Yeah, but the inputs would be address 1's address, user 1's address, and that balance.
Right, but it's not a form of like obfuscation of like who was transferring anything.
No, you can you could be able to ascertain like who did what, right? And so just a quick demo to like show you some resources that you can use. So this is a standard. So this is Bancor's code, right? It's all up here. It's all on GitHub. And generally, if you don't see people open sourcing their code, it's a problem, right? Why are they hiding their code from you? Anyway, so we've got Bancor's entire GitHub repo right here, and this is their interface, right? For ERC20 compliant tokens, and they've got all the methods, right? They've even got the human standard stuff: name, symbol, decimals, etc. Okay, so if you go into contracts and you go down to ERC20, you can see them implementing the interface. Right? So all the resources are here for your project. Furthermore, this is what I was talking about with Etherscan. So if we go back here, you can see all the ERC20 compliant tokens. If you click on one of them, okay, you can see all the details, all the transactions done with them. And then you can click on their contract address and also look at their source code over here. And this is why it's so useful. So you'll notice one more thing, right? This safe math library, or let's see, pausable token, right? These are not things that they've written, right? And that's fine because they've implemented from other libraries. And that library is OpenZeppelin, where you'll see pausable token, mintable token. And so if you want to implement any of these extra versions of tokens, you're more than welcome to. And so you can go into these in your own time and find out what they do, or ask questions on Piazza, and we'll be more than able to like help you out. But these are all interfaces that you guys can use. I highly recommend Safe Math because we talked about security last week. It helps get rid of all those problems with overflow and whatnot. So you don't have to worry about them. Burnable token, right? Et cetera, et cetera. All right, any questions on that? Yep.
So are like addresses for the ERC20 tokens, are those all really just like Ethereum account addresses?
Yeah, so tokens are generally built on Ethereum, and the ERC20 standard only applies to tokens built on Ethereum. So like things like IOTA, that have their own quote-unquote blockchain. It's actually a blockless blockchain, but why not? Whatever. You wouldn't consider those ERC20 compliant, but you wouldn't even ask that question because they're not Ethereum-based tokens. Questions? Okay. So one more thing I want to add. Despite everything, ERC20 doesn't fix the issue of burning tokens. Tokens are still lost when sent to contracts that can't account for tokens. Right? And so this is why some 200 ERCs later, we have ERC 223, which aims to fix that. All right, so this is not that important. It's just a thing that exists. Extra credit if you want to make your midterm project ERC 220, 223 compliant, but you don't have to. It's just out there. And this aims to fix that problem of losing your tokens when sending them to contracts. What's up?
So, I mean, do they approach solving the problem from the tokens perspective or from the contracts perspective?
So what do you mean by that?
Like, are there requirements that contracts need to implement certain functionality for receiving tokens, or is there requirements that tokens have some sort of like bounce back mechanism if they don't receive credit?
Yeah, so with tokens, tokens are kept track of on the contract. How many tokens anybody has at any one time, that's all documented on the contract. So it's not like the token has a physical form on the Ethereum platform. So anything you do with your ICO should go on your contract. Does that answer your question?
Yeah.
Awesome. Okay. If there are no more questions, please sign in. Code word is HypeTrain for today. URL is really easy, just devdecal5. I'm going to pass it off to Akash to talk about smart contract architecture.
Oh, HypeTrain.
All right. Cool. I'm a little sick, so my voice is going to be a little shit, but we'll make it work. So we're going to talk about smart contract architecture, and we're going to talk about how to build like scalable backends, basically. So this is what you think about when you're not thinking about decentralized applications. You're thinking about building, how do I build this backend that can scale? We need to think about it here for smart contracts as well. So the systems that we're going to study here, smart contracts are actually designed to be modular. You deploy them on the blockchain, and you notice that everybody's putting things in different contracts for good reasons. And we're going to talk more about that. Basically, for trust, you need to be someone needs to be allowed to make like updates for these contracts. So note that when you're thinking about security, when you're thinking about needing to patch things and making scalable systems, you need to be able to make updates, and that requires trust. So we can think of smart contracts as services. Basically, smart contracts are going to be these stateless web services that you can work with. And web services, we can think of them as units of functionality in a system like the internet. They have well-defined APIs that you can call from. And then they have identifiers, such as IP addresses, that can be used to like target them when you make your calls. So a smart contract is just like this, where Solidity contracts are the public API, and the public address is going to be the identifier in this case. So you can make a lot of parallels, as you can see. So web service is called by making an HTTP request. A Solidity smart contract is going to be called by making a transaction on chain. So since endpoints are exposed in like the web, you need to handle your security by call basis. So if you've ever worked with like a REST API before, you'll notice that there's like GET, POST, and all your different requests. You need to handle each of those calls on a call-by-call basis for security reasons. The same goes for like smart contracts. You need to know like where your calls are going, what's happening to each of them, how they're going to change each contract. And this is why we kind of put things in architecture formats for smart contracts. So you can kind of model this similarly to how we model things in regular systems using the microservices architecture, where basically you break things down into independent deployable components. So if you've ever like interned at a company or something like that, you'll notice that they have a ton of like things going on with their projects. They're going to have a lot of different services for like their databases, their APIs. All their infrastructure is going to be like distributed in some way amongst their teams. So we need to have like a similar philosophy when dealing with smart contracts, because this is how we do things in the professional world. So every like non-trivial DApp is going to have more than one contract. We saw that with Parity. You can't write secure and scalable smart contracts without distributing the data over multiple contracts. So you have to kind of compromise between one or the other. You can technically make it more secure by writing it in one contract. However, scalability starts to become a problem with the amount of code you have to write. And multi-sig wallets aren't that complicated anyways. So that's not really something that's more than trivial. So instead of thinking about like what these contract systems do, we should think about in terms of what they are. So let's not just think about the functions, but let's think about the communication between each of these contracts. So I'm going to introduce the 5 types model, and there's 5 components, which is why it's called 5 types. You're going to have database contracts, controller contracts, contract managing contracts, application logic contracts, and utility contracts. So one thing to keep in mind is that this stuff is all new. There's no single right way of building smart contracts. So like these philosophies are up for debate, because even Solidity is not like that robust of a smart contract language. It's going to be replaced in the future, at least in my opinion. So we're going to start with contract managing contracts, because this is kind of where the highest, like, I guess, king of the stack is in this architecture overview. So contract managing contracts, these are contracts that are going to just manage other contracts. They keep track of all the components between the system, and they're going to communicate between multiple contracts. This is going to make your modularity easier. And if you note the contract above, it's called Doug. I don't know how well you can see that, but basically this is the contract that's going to add instances to your contracts. So it's going to keep track of all your contracts instances in like a mapping, and it's going to be able to handle different functionality, like adding to that mapping, removing from that mapping. It also is going to interact with different components in the whole system that we have going. So you notice that we have like a permissions DB, we have a bank DB. Basically, the remove function ends up removing from those as soon as like we remove an instance from the contract. So it's just going to manage the whole overview. And yeah, these can get pretty complicated. Like there's like 4 different contracts just to like manage other contracts. So you can make this pretty complicated. You can simplify it. But for this example, we're gonna be like kind of constructing a bank, and essentially we're going to like break it down into like 5 different components. So database contracts, these are going to store like all your data. These contain functions that allow other contracts to write and update and get data. You also must be able to check permissions for this data. So you don't want certain people to be able to write your data. You don't want certain people to be able to read your data. And you only want certain people to be able to do like both. So you need to keep track of these in some kind of a mapping. And usually you have like a permissions database contract that you can use. And you can just set permissions to an address and store those, store a mapping between like addresses and permissions. So also you're gonna have multiple databases in your contract. You're gonna be having storage for your application, but you're also gonna be having storage for your permissions. And those are most often gonna be like your 2 database contracts.
You also have your controller contracts. How many of you guys heard of MVC? Okay. How many of you guys are familiar with how an I/O controller works? So this is like pretty similar. Like at the end of the day, like a controller in most contexts is just referring to how you operate on like data, how you operate like in and out. So this can basically allow for you to do like special reads and writes. So you can do batch read and writes. You can do multiple read and writes to different places. You can like set multiple permissions at once while reading and writing. All that like complicated stuff that you want to do with your storage, you kind of do in your controller contract. There's kind of like an edge between controller and application layer, because you can imagine there's like some overlap. We'll kind of talk about that, but basically an application contract is going to contain, yeah.
So I was just wondering, sort of akin to like the internet analogy, like now if you're building an application on the internet, then you would make use of some kind of like third-party database typically, and then unless you're like a huge corporation, then you might have it in-house. So like if you're developing a distributed application, is there sort of an analogous third party that might be writing those?
That's a really good analogy actually. There are different like type. There's APIs that handle like kind of like your database for you. There's something called Lisk, which like it's a JavaScript API for like working with like blockchain, which is your database. Yeah.
Wait, but the only kind of persistent storage will be on the blockchain itself, right?
Yeah.
So, well,
Well, yeah. I guess the
There's
smart
no way to
contracts.
interface like between the blockchain and some other third-party database on the web.
Not that
Maybe
I
that's a stupid question.
Not that I know of. I mean, the only interface is going to. You could make a DApp that does that, but
You can do it with like Oracleize it, I think, allows like HTTPS requests.
That would sort of
oh, that's different.
But
Though. That's more
that's-
like
yeah.
more like calling. Like that's making like external calls.
It would kind of defeat the purpose
yeah.
of the whole system.
Yeah. Any other questions? Okay. So application logic contracts. This is pretty self-explanatory. All this means is that you're going to put all your application-specific code here. So that means, in this case, we have the bank, and the bank is going to interact with the bank database. So if you want to like make changes like by depositing or withdrawing, you need to make those updates. You can do this using the bank application logic. We also have utility contracts, which are libraries. You can think of these as the string like concatenation, or you can think of these as like random number generators or stuff like that. This is just, you're going to call these from like any contract within this whole framework, depending on the use case, but these should just be available if you need them. So this is an optional one. So this is what the contract looked like with 4 or 5 types. We have a bank contract. It's pretty simple. You have your set owner, you have your deposit, and you have your withdraw and your remove function. And you also have a fund manager, which is going to handle all instances of the bank. And our modularity kind of changes as of such. You'll notice that there's a much more clear separation of concerns on the right compared to the left. And this is generally better because if you have a much more clear separation of concerns, it's much easier to update the component that fails. And it's also much easier to track down your bugs. Yeah.
So if I go like Banker's GitHub, would I see examples of structure more or less?
Which GitHub?
No, like if I go like Banker's GitHub, would I see like the same?
Oh, I don't know about
structure?
Bancor.
Oh, just like in general.
But other ones, yeah. So I actually have access to like a few like smart contract audits that I shouldn't have access to, but they actually laid out pretty similarly. They won't use like the 5 types model, but they'll use something that's relatively like similar and modular, because it's pretty opinionated about how you can go about this. The reason why I'm teaching you like 5 types is because it's good to know like what's out there. So is this like worth doing? Like, if I just want to deposit some money, like why do I need to go through all these contracts that call other contracts that keep calling other contracts? there's some things that you should like keep in mind, which will make this worth doing. So modularity is good, and even though all this indirection means more calls and processing, this is gonna require more cost to store the code on chain, but also to execute the code for all this modularity. It's also harder to write secure smart contracts, but this modularity is important if you want that upgradability aspect. So 5 types was good in theory. It had a really good separation of concerns. It was very modular. It was capable of handling permissions, which you don't usually see in most smart contract frameworks, handling permissions. So here's a big problem. Like, what if we have 10 controllers, 10 databases? On average, each controller can have 4 functions in its API call, in its public API. And that means you're going to have 40 functions just for the application logic. So on top of that, each time you're going to update the system, you have to replace the whole application logic. So this is going to defeat the purpose of modularity entirely. Modularity is good in programming context, but when you're deployed on chain, it's good in the upgrade context, and you don't want to lose that because you shouldn't really care about the developer context as much as you do about the deployment context, because the security of being compromised is much worse than having developers have to deal with shitty code. So we have 2 possible solutions for dealing with this in the 5 types model. You can divide the application logic into multiple contracts, or you can omit the application logic and you can instead add multiple controllers that we just call directly. These are both okay, but again, we still break the whole upgradability aspect, because now you don't have you still have to replace entire contracts to do minor changes to the logic. So that's still problematic. So an action-driven system is going to do everything through action contracts. It can contain any logic, and normally they're going to be fairly small and focus on a few things. So you'll divide up all your actions, and I'll show you how that looks. They have access to the DUG contract, which is, remember, the DUG contract is going to manage all your contracts on chain. And just like normal contracts, they have access. But validation is not going to be done through the DUG contract. It's going to be done through the action manager, and I'll talk about that. You'll notice that we're kind of cheating here because we're adding the actions map to the action manager itself, and that's bad for certain reasons. And in the diagram, we kind of skip over a lot of detail. We don't really show for example, we don't show all the controllers. We just show an action manager and its actions. But the idea is that we're going to have a lot more modularity, and the final contract is going to be kept in the database contract. So action-driven architecture, you can see here that we have an action manager, and we have all our different actions. You can add a user, remove a user, pause it, and drop. And you also have these are basically call dependencies for the user DB and the bank DB. And the action manager is basically going to handle all the actions. Does that kind of make sense? Yeah.
So are each of the actions a different contract?
Yeah. Yeah. Well, which one are you first?
Go first. What is the DB?
What is the DB?
Something.
So DB is just going to store all the user
On the
data.
ED and that one?
Sorry?
On the ED and that one?
Yeah.
It will be just a stream or...
So it's going to be a contract. It's going to be a contract with
So it's not a real database, right?
Sorry?
It's not a real database.
No, it's not a real database. So keep in mind that all this architecture is abstracted into contracts.
So if you say there's something wrong with your deposit action, you would deploy a new deposit contract and then update your action database to point to the new one?
Yeah.
That's how you upgrade this architecture?
Yeah. We'll talk more about upgradability pretty quickly. But yeah. So basically, action-driven architecture, here's a few things to keep in mind. You have good, flexible creative management. Contracts themselves are not like good dividers, but if you think of them in terms of actions, then it's not as bad. Instead, you should think about managing actions, not necessarily contracts. You have a unified interface, so all the actions work the same way. This makes UI generation pretty easy later on. These are also fully extendable, so that means individual actions can be added or removed without affecting the entire system. And it's expensive, so there's a lot of code in contracts. But so doing action-driven development is going to cost you more, so it's not good in production environments. So this is what it would look like for a bank. I'm not going to go through all the code because that's going to take too much time. I'll give you a reading that kind of goes over it. And yeah, like I said, it's all in progress. We're going to talk DApp architecture next time because we're going to go over Web3. This was smart contract architecture. This is just talking about how to distribute your smart contracts in your backend. Now we have to zoom out and start thinking about, okay, now how do I interact with my backend with my front end, which is easier in my opinion. And I'm going to briefly go over upgradability. Sorry guys, I'm going to hold you for 5 more minutes. Basically, code needs to be changed if errors are discovered or improvements need to be made. If I find that I'm wasting a lot of gas on a certain function, or if I find that there's a security flaw, if I don't have a way to deal with it, that sucks. My contract's stuck on there, and I can't do anything about it. But if I set up things for upgradability, then I can do something about it. So designing this upgrade system is pretty cutting edge. It's kind of hacky in some ways. It's not like Selenium was designed to do this, but it works. So there's two basic approaches. We have a registry contract, which is going to point to the latest version of the contract. And then we have another contract, which is going to forward calls to a new version of the contract. So the difference between these two is that registry is more simpler, and the delegate call version, the forwarding call version, is going to be more seamless. It's also important to note that you need a secure way for parties to upgrade the code. So generally, you're going to trust some parties to do this. So if it's the ICO that invests in, yeah.
What does more seamless mean?
More seamless?
Yeah, why is that? Why would it be more seamless than just replacing code?
It's more seamless because you don't replace code. You simply just point to a new you simply just delegate call to the new contract. I'll show you the code. You'll see it. Yeah. So you have to think about trust in this context. So there's a way to do it trustlessly where people can kind of vote on whether to upgrade this contract. We won't talk about that here because that's way more complicated. But in general, you're trusting someone when you implement contract upgradability. If this process is going to take some time, you want to consider you want to have some backups if you get attacked. So there's two ways of doing this: is emergency stop and a circuit breaker. We'll talk about those as well. So this is the registry contract fix. Basically, I have an array of my previous backends and have my backend contract. All I'm going to do is I'm going to have a function called change backend, and it's going to allow me to update the contract when needed. Pretty simple. So there's two main disadvantages though. So one thing is that the user has to always look up the current address, and anyone who fails to do so risks using an older version. And you also need to think carefully about how to deal with the contract data when you replace a contract. I'll kind of talk about why that's a problem in the next slide, because specifically the next fix is actually much more problematic with data. Because you can imagine when you upgrade a contract, if you change some variables, how do you deal with that new mapping of variables? You can't really, right? You can't really have a previous contract that somehow predicts what's going to happen next. However, as you remember from the Selenium Dev lecture, there is a mapping called storage, which contains all the persistent variables. And if you just take all those variables, you can probably write a function to carry over some of those variables and remap them in your new contract. But then you have to write that logic in your new deployed contract. Does that make sense? Okay, so this is fix number 2. So the focus of this is like you forward the data using delegate call, and you have to be pretty careful about how you deal with storing data in this contract. Basically, if your contract has a different storage layout, your data is probably going to end up corrupted, because you have to think about like how the variables are stored, or how all the data structures and like function mappings are like stored in like the EVM. It's likely with a delegate call, it does things very differently. I won't like break it down here, but just remember that this is sort of a more dangerous method than the previous. Delegate call, remember, as in the parity attack, it kind of gets confusing. It takes the state of it basically takes the state of the current, wherever the current function is that you delegate call from, it's going to take that contract state, and then it's going to carry it over to where you delegated call from. So that's why it's likely that your mappings are going to be fucked up. So circuit breakers, these pause contract functionality. So this isn't really like about upgradability, but this is more like how you transition to that upgradability, right? When things go wrong, like how do you make it so that you have time to like upgrade? And a circuit breaker is one of these ways. Pause the contract functionality, and these are going to stop if certain conditions are met, and if a bug is discovered, you can suspend like your like actions on the contract, so you can suspend certain functions, you can kind of lock them. And you can also give like certain parties like trusted access if you want to. So if you don't want to close everyone out, or you want to like lock certain people out that like want to be able to call certain functions, you want to like disable maybe like the withdraw time for like certain like groups of people, but not everyone. Like for example, if important people are using your contract, and you don't want to lock them out, you can choose not to lock them out. And you can also have certain programming rules that are going to automatically trigger the circuit breaker when these like conditions are met. So this is what one looks like. I won't like spend time on this because I think it's pretty self-explanatory. Speed bumps, these are going to delay your contract actions. If malicious actions occur, this is going to put a lock on the time that it takes to like perform a function. For example, the DAO would require like 27 days to like split the DAO. And remember that splitting the DAO was used in the attack. So, the hacker could not like get access to the funds for 27 days, could not call a withdraw function. In the case of the DAO, this is kind of useless because what can you do really? Like, you already like managed to get a hold of the funds. So, but if you combine this with other techniques, it can be pretty effective. So this is what it looks like. Basically, I set the withdrawal wait period to 28 days, and in request withdrawal, I can, I do my normal checks, but along the way, I also check for the withdrawal period. Or sorry, in withdrawal. That's where we check for the withdrawal period. Yeah, any questions? Okay, so, whatever the technique is, it's very important to have separation of components. You don't want like your code changes to break functionality or create orphan data or require like very high costs to like port over. And it's very beneficial to separate your complex logic from data storage, so you don't have to recreate all the data to like change the functionality. So it's good to have that. It's good to have like that like mapping of data that like makes sense when upgrading, so that like you don't end up changing a bunch of your variables. So if you plan well ahead, then it's like much easier. Otherwise, your new contract has to handle all the variable changes that you do using the storage like mapping that you have. Yeah. And next time we're going to talk about Web3.js and interfacing with the blockchain. We're also going to talk about writing a test suite with Web3 and Truffle. I know Home 2 like testing suite was a little difficult. will make it like much easier to do. Talk about deploying to testnet, and we're going to talk about like making an initial front end with the new abilities of Web3. Yep, that's it.
Any homework?
We will have homework, yeah.
Right now?
No. Yeah.